Let's do it. Class N. Share my screen. Class N. There we go. Class N. So we're going to talk about some trig identities. Specifically, the quotient identities, which just means the ones that look like fractions. We've already kind of talked about those, but we want to make them a little more formal. And the Pythagorean identities. Pythag, I can spell Pythagorean identities. And then lastly, we'll have some examples where we kind of, and then I will say the last thing will be is using trig identities to simplify. To simplify expressions. That's what we're doing today. And hopefully I won't take too long to do it. Sure, one line, that one too. Why not? Who cares? All right, so let's start with the quotient identities. So you kind of already know the quotient identities. They really do come from, I mean, really just the way we define the trig functions. You can also think of them from the unit circle. So good to see the unit circle again. Let's go ahead and draw ourselves a little unit circle here. Again, the defining feature of the unit circle is that the radius of the circle is 1. So that's the point 1, 0. That's the point 0, 1. Negative 1, 0. 0, negative 1. Don't really care about these points, but it seems good to draw them. And then we draw some, oh, they move this the other way here. Then we draw some angle. It's not any specific angle. We just say that that's theta. We drop our perpendicular to the x-axis. And this side here is x. This side here is y. This side here is, of course, is 1. And this point here is x comma y. But if we look at this, we can see that, oh yeah, cosine of theta is x over 1. I know I'm doing this out of order. I'm going to fix it. Don't worry. I would have done sine first. Sine of theta is y over 1, which is just y. Tangent of theta is just opposite over adjacent, which is y over x. And then the reciprocals. Cosecant of theta is the reciprocal of sine, so it's 1 over y. Secant of theta is the reciprocal of cosine, so it's 1 over x. And cotangent of theta is x over y. When I think of the quotient identities, what I'm really thinking about is the fact that each of the trig functions other than sine and cosine can be written as a fraction involving sine and or cosine. For example, tangent of theta equaling y over x is just equal to sine of theta divided by cosine of theta. In a similar way, cotangent of theta equal to x over y is just cosine of theta divided by sine of theta. We can also talk about secant and cosecant. Secant of theta being 1 over x is really just 1 over cosine, or the reciprocal of cosine, which we've said like 1,000 times. And cosecant of theta being 1 over y is just the reciprocal of sine. It's 1 over sine of theta. So these are the ones I typically keep in mind. There are 2 more I will mention, although they're used less often. But the 2 other ones that sometimes come up is that you can also say that cosine of theta is the reciprocal of secant. So cosine of theta is going to be kind of weird. It's going to equal x, which is 1 over x, which is just 1 over secant. And you don't really need these intermediate steps here. And similarly, sine of theta, I had little dots here. I should have little dots here too. Little dots. Sine of theta, you could think of as y, which is 1 over y, which is 1 over cosecant of theta. So basically, oh, actually, there is one more I should talk about. Basically, if things are reciprocals of each other, you can always write each one as 1 over the other one. So since secant and cosine are reciprocals, you can write secant as 1 over cosine, or cosine as 1 over secant. Since cosecant and sine are reciprocals, you can write cosecant as 1 over sine, or sine as 1 over cosecant. And lastly, and I should have included this one before, in addition to being able to write tangent as y over x, which is sine over cosine, you can also think of tangent of theta as the reciprocal of cotangent of theta. Right, tangent of theta is y over x, and cotangent of theta is x over y. So 1 over x over y is just y over x. And similarly, cotangent of theta, although I usually prefer to think of it as cosine over sine, you can also think of it as 1 over tangent of theta. So these are the quotient identities. They're how you can write trig functions as fractions of other trig functions. They're not particularly more useful to find or evaluate trig functions of specific values. For example, if I wanted to find, say, tangent of, I don't know, 5 pi over 6, I'm really just thinking of it, well, here's my reference angle. Sorry, here's my triangle for my reference angle. My reference angle is pi over 6. That's a 30-degree angle. The opposite's 1. The adjacent's root 3. The hypotenuse is 2. So I might think of tangent of pi over 6 as 1 over root 3. Or you might think of it as, sorry, I should have said 5 pi over 6. You might think of it as sine of 5 pi over 6 over cosine of 5 pi over 6. Sine of 5 pi over 6 would be opposite of hypotenuse, so 1 over 2. It would be positive 1/2 because 5 pi over 6 is in quadrant 2. And then cosine of 5 pi over 6 would be adjacent over hypotenuse, so it's going to be negative root 3 over 2 because we're in quadrant 2. And then you can flip and multiply and say you've got 1/2 times 2 over negative root 3. The 2's cancel. You get negative 1 over root 3, which is negative root 3 over 3. Not really better, right? I would rather just say tangent of 5 pi over 6 is negative 1 over root 3 and then rationalize it. So this is not really, we don't really use these quotient identities to help us evaluate trig functions of specific angles. What we do use them for is to help us simplify expressions involving trigonometric functions. Let's talk about the other trig identities. And actually, we'll start with some examples there. So let me just draw any old right triangle and give myself some sides. So say we have this triangle. Let's say, I don't know, this side's 5, this side's 4, and using the Pythagorean theorem, this third side should be the square root of 25 plus 16, which is 41. Let's call this angle theta. We can check, right? 4 squared plus 5 squared equals the square root of 41 squared. 4 squared is 16, 5 squared is 25, square root of 41 squared is 41. Yep, that checks out. Okay. So what I want to show you here is one of my favorite identities. It's actually what I usually call the most famous trig identity. So let's find sine of theta. Sine of theta is 4 over the square root of 41. I'm not going to rationalize it. Cosine of theta is 5 over the square root of 41. Here's what I want you to see. And this was definitely a bonus problem of like a week ago or so. So sine squared theta is just sine of theta, quantity squared. And cosine squared theta is going to be cosine of theta, quantity squared. So that's going to be this quantity here, 4 over root 41 squared. Cosine of theta is 5 over root 41. We're going to square it. And let's see, 4 squared is 16. Square root of 41 squared is 41. 5 squared is 25. Square root of 41 squared is 41. 16 plus 25 is 41. So we get 41 over 41, which is equal to 1. It's not a coincidence. It's true no matter what triangle or what angle we picked. For example, let's say we wanted to pick an angle in, I don't know, quadrant 3. Let's say we picked, I don't know, 4 pi over 3. So let's do the same thing. If I find, let's put in the box here, sine squared of 4 pi over 3 plus cosine squared of 4 pi over 3. Well, I'm going to rewrite an extra step here. That's going to be sine of 4 pi over 3 quantity squared plus cosine of 4 pi over 3 quantity squared. That's going to equal, let's see, so I now need my triangle. So my reference angle is pi over 3, which is 60 degrees. Opposite's root 3. Adjacent's 1, hypotenuse is 2. Or you could do 1/2 root 3 over 2 and 2 over 2, which is 1, whatever you like. So then sine of 4 pi over 3, well, 4 pi over 3 is in quadrant 3, so sine is going to be negative. So is cosine. So I'm going to get negative root 3 over 2 squared plus cosine of 4 pi over 3 is going to be 1/2, so it's going to be negative 1/2 squared. Now, whenever you square something, whether it's positive or negative, it ends up being positive as a result. A negative number squared is a negative times a negative, which is positive. A positive number squared is a positive times a positive, which is positive. So whenever you square something, you always end up with a positive result. So here we're going to get, well, let's see, positive square root of 3 squared is 3, 2 squared is 4, plus positive, I'm not going to write positive again, 1 squared is 1, 2 squared is 4, and 3/4 plus 1/4 is 4/4, which is 1. So here's the abbreviated version of this. Well, in fact, it's not surprising if you think about the unit circle again. Let me draw a real quick one here. So this is my unit circle, and there's my angle theta, and this side is 1, and this side is x, and this side is y. It is totally true that, well, Pythagorean theorem, that's why they're called Pythagorean identities, that x squared plus y squared is equal to 1. But also, we know that x is cosine of theta, and y is sine of theta. I didn't write 1 squared over here because I know that 1 squared is equal to 1, but technically that's a 1 squared. I just simplified it in my head. So I can technically write this as cosine squared of theta plus sine squared of theta equal to 1. I mean, again, just to make sure everyone's on board with this, when I'm writing cosine squared of theta is just an abbreviation for writing out cosine of theta quantity squared. And similarly, sine squared of theta, same deal. Whenever you write something, a trig function squared of an angle or whatever power you want there, it's just because I don't want to write sine of theta quantity squared. You can use parentheses, brackets, whatever you like, but I'm just going to write it this way because it's easier. So this is how, so you can write this way. I usually prefer to write it with the sign first. I don't actually know why, I just do. So I like to write it as sine squared of theta plus cosine squared of theta equal to 1. And again, that's what I call the most famous trig identity or the most well-known trig identity. And then there's also 2 alternate versions of it. If I subtract sine squared from both sides, I get cosine squared of theta equal to 1 minus sine squared of theta. And then the other way is this, if I subtract cosine squared from both sides, I get sine squared of theta equal to 1 minus cosine squared of theta. All right. There are 2 other, where's my timer? Sorry. Where'd my little control thing go? There we go. No. So I've lost all control. Oh, well, I just won't know how much time I spent. It's not like it's going to stop me from going as long as I want. Okay, so these are often used. Let's talk about another. So there's 2 other Pythagorean identities, which really are just stemming from the Pythagorean theorem. So let's do the one with tangent. Tangent is kind of my favorite one. There's a reason why. So let's look at another triangle. No, not any old triangle. Yeah, any old triangle. Let's say we've got any old triangle. Let's make the sides a little nicer just because why not? Let's pick everyone's favorite right triangle, the good old 3, 4, 5 right triangle. And let's call this angle alpha just to change it up. So instead of looking at sine and cosine, let's look at tangent and secant. So remember, tangent is opposite over adjacent. So tangent of alpha is equal to 3/4. And secant, I never remember secant. I do remember that secant is the reciprocal of cosine. I know that cosine of alpha is adjacent over hypotenuse. So it's going to be 4/5. So secant of alpha must equal 5/4. So now check this out. I'm going to say that 1 plus tangent squared of alpha. Let's calculate that. That's going to be 1 plus, let's see, tangent of alpha is 3/4. Quantity squared. Let's see, 3/4 squared is going to be 9/16. And the reason I didn't write the 1 yet is because I might as well change 1 into a fraction who's got a common denominator. So let's make that 1 16/16. And then 16 plus 9 is 25/16. 16 plus 9, 16, 25/16. And then finally, that is equal to 5/4 quantity squared, which is secant squared of alpha. So here is the next trig identity. it is 1 plus tangent squared of, pick whatever angle, like usually people use theta, is equal to secant squared of theta. Okay. Now here's why this one's my favorite, because it's unforgettable. One time years ago, a student said, oh, here's how I remember that. They remember this as quote unquote, I for one, tan and get sexy. Now I do not tan, I burn, but the point is you've got I for one, tan for tangent, get for equals, sexy for secant. So 1 plus tangent squared equals secant squared is I tan and get sexy. It's kind of hard to forget once you hear it. I think I've never forgotten it. So 1 plus tangent squared theta equals secant squared theta is another trigonometric identity. And it is a Pythagorean identity. It also comes really just from the unit circle again, right? If I draw myself a little unit circle here, I'm going to do the same sort of thing. There's my theta. And I can say, okay, well, this is still x, this is still y, this is still 1. 1 plus, well, let's see, tangent of theta is going to be y over x squared. That's really going to be, this is looking interesting here. I don't know about this. So that's going to be x squared over x squared, right? You made 1 x squared over x squared plus y squared over x squared, which is equal to x squared plus y squared over x squared. Oh, but x squared plus y squared is equal to 1 squared because of the Pythagorean theorem. This is really equal to 1 over x squared, which is 1 over x quantity squared, which secant is 1 over x. This is totally secant squared theta. So that's actually why it's working. And I guess I should have started with 1 plus tangent squared. Sorry about that. Sorry, I feel like I'm writing really, really small here. Let me zoom in just for a minute. Whoops, I tried to zoom in and my camera did something bonkers here. I don't know what just happened. I think I loosened my cord or something. See if I can fix that. That is terrible. Wow, that's really great. Did I just break my camera? Let's try turning it off and turning it on. Jeez. It's gonna be a real bummer if I broke my camera mid-class. Dun, dun, dun. Let's try closing the visualizer. Okay, let's try opening it back up again. Hopefully that works. I have to cut this part out. Oh, good. We're back in business. I know you're all worried. Okay, so let me share my screen again. Well, I was trying to zoom in to show you all the work I was just doing. Let me click off of this so it doesn't look quite so heinous. I was trying to show you all this down here, that in this, unit circle such situation, 1 plus tangent squared theta is really 1 plus y over x squared. 1 becomes x squared over x squared. Y over x quantity squared is y squared over x squared. Add them together, you get x squared plus y squared over x squared. But because of the Pythagorean theorem, x squared plus y squared is equal to 1 squared, which is just 1. So this becomes 1 over x squared, which is 1 over x quantity squared, which is secant squared of theta. So it totally works. Let me show you another way of getting there, and then we'll talk about the last one. Sorry, I know it's a little wobbly there. I don't break my camera again. Okay, so let me refocus here. In a similar way, you can manipulate this, but they're like nobody ever really writes secant squared minus tangent squared equals 1. Or I suppose people do write the other kind of version of this is subtracting 1 from both sides and writing it as tangent squared theta equals secant squared theta minus 1. Another way we could have gotten here is by starting with the favorite, everyone's favorite trig identity, most famous trig identity, sine squared of theta plus cosine squared of theta equal to 1, and dividing everything by cosine squared. So if I divide by cosine squared, what do I get? Well, I get sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equal to 1 over cosine squared theta. I'm going to rewrite this as sine of theta over cosine of theta, quantity squared. Cosine squared theta divided by cosine squared theta is just 1, right? Anything divided by itself is just 1. And 1 over cosine squared is 1 over cosine of theta quantity squared. Sine over cosine is tangent. So this is really tangent theta quantity squared, or tangent squared theta, plus 1. And 1 over cosine is really just secant squared theta. And then I would never write it this way. I would never write tangent squared plus 1 equals secant squared. I would always write it as 1 plus tangent squared theta equals secant squared theta. Or I tan and get sexy. All right, it's pretty clever. Nah, it's not that clever, but I didn't come up with it, so I can pretend like I can say it's clever because like it wasn't my discovery. Let's do the same thing if we have enough room over here for this, but instead of dividing everything by cosine squared, we'll divide everything by sine squared to get the last trigonometric Pythagorean identity. So if we divide the entire identity by sine squared, can I write? Maybe. Let me zoom in so you can see what I'm writing. So then if we divide everything by sine squared, we get sine squared theta divided by sine squared theta plus cosine squared theta divided by sine squared theta equal to 1 divided by sine squared theta. Of course, sine squared theta divided by sine squared theta is just 1. Cosine squared theta over sine squared theta, we could rewrite as cosine of theta over sine of theta quantity squared. Similarly, 1 over sine squared we can write as 1 over sine of theta quantity squared. And then cosine over sine is cotangent. So that's cotangent squared of theta. And 1 over sine is cosecant. So this is the other Pythagorean. And you can write it like this, which is standard, or you can subtract 1 and write it as cotangent squared theta equal to cosecant squared theta minus 1. These identities do not come up as much, these cotangent, cosecant ones. These tangent and secant ones, or the other way around, tangent squared theta equal to secant squared theta minus 1. These two come up much more often than these two do. And of course, the one that comes up the most often is sine squared theta plus cosine squared theta equals 1, or, sorry, you can't see that, or cosine squared theta equals 1 minus sine squared theta, or sine squared theta equals 1 minus cosine squared theta. This one and its versions, and these two are more popular than these two. When I was working at UCCS, University of Colorado, Colorado Springs, my students tried to come up with an equally good saying for this one, equally good as I tan and get sexy. We came up with something, it wasn't quite as good. They came up with I sleep on a cot in Colorado Springs, Colorado. Not as good, but kind of memorable if you live in Colorado Springs, Colorado, which we don't, hey, whatever. Okay, so those are the identities that we should be aware of. Let's list them out again. Just let's do a few examples and then we'll list them. We'll list them at the very end. So a couple things you can do with triidentities. If you can simplify expressions so that they don't take up as much room. For example, we want to simplify down to one term. What have I got here? I've got 1 minus sine of theta times secant of theta plus tangent of theta. Now be careful, 1 minus sine is not equal to cosine. 1 minus sine squared theta is equal to cosine squared theta, but 1 minus sine of theta does not equal cosine theta. Let me give you a quick example of that. If my theta were, say, to be, I don't know, pi over 3, 1 minus sine of pi over 3 is 1 minus the square root of 3 over 2, which is 2 minus root 3 over 2. But 2 minus root 3 is not equal to 1, right? 2, right? In fact, it's negative. That definitely does not equal sine of pi over 3. Sorry, cosine of pi over 3. Apologies there. Which is equal to 1/2. So 1 minus sine of pi over 3 does not equal cosine of pi over 3. And 1 minus sine of theta does not equal cosine theta. But 1 minus sine squared of theta definitely equals, sorry, 1 minus sine squared of theta definitely does equal cosine of theta. Cosine squared of theta, oh my God. 1 minus sine squared theta equals cosine squared theta. Okay, so the idea here is we want to take this expression and try to make it look like something with just one term. So we're going to multiply it out. Yeah, we're going to multiply that. Yeah. So we could either, so my kind of thought process for these is either to do the multiplying first, so FOIL it out first, or to write things in terms of sine and cosine and then do stuff. I'm going to just multiply this out first, see what happens. So I'm going to FOIL. 1 times secant is secant. of theta. 1 times tangent is tangent of theta. Negative sine times secant. Okay, that doesn't look nice, but I've got negative sine of theta times secant of theta. And then negative sine times tangent is, minus sine of theta times tangent of theta. Yeesh. So this is where I always kind of fall back on writing things in terms of sine and cosine. I'm going to write secant as 1 over cosine of theta. Tangent is sine of theta over cosine of theta. Secant is 1 over cosine. So I really have got minus sine of theta times 1 over cosine of theta, which I should really just write as sine over cosine. Then I've also got minus sine of theta times tangent, which is sine of theta over cosine of theta. So let's see. The sine theta over cosine theta minus the sine theta over cosine theta, those cancel out. Or they add to 0. So I'm left with 1 over cosine theta minus sine of theta over 1 times sine of theta over cosine theta is sine times sine is sine squared theta over cosine theta. Lucky me, I've got a common denominator. So I can write this as 1 minus sine squared of theta divided by cosine of theta. 1 minus sine squared is equal to cosine squared of theta. And then when you have something squared divided by itself, like 3 squared divided by 3 or 6 squared divided by 6 is just 6. 3 squared divided by 3 is just 3. X squared divided by x is just x. Cosine squared divided by cosine is just cosine of theta. So that's kind of the idea, is we can take an expression and multiply it out, simplify it down, use trig identities to make it look nicer. Let's do 1 or 2 more, and then we will call it a day. Yeah, 1 or 2 more. They're a little gnarly, but that's life. Sometimes you get gnarly things. Let's look at this one, which is less gnarly. Let's start with, is that one right? Sure. Yeah, so we'll do this one. Let's do secant of alpha times cosecant of alpha minus tangent of alpha. We want to, again, the idea here is we want to re-express this or simplify it in such a way so that it can be just one term. And again, I'm going to fall back on sines and cosines. So secant is really 1 over cosine of alpha. Cosecant is 1 over sine of alpha. Tangent is sine of alpha over cosine of alpha. And I can see that if I try and add these two fractions together, this denominator here is cosine of alpha times sine of alpha. This denominator here is just cosine alpha. So I'm going to need to multiply this by sine of alpha over sine of alpha. Okay, so now this is going to be 1 over cosine times 1 over sine is just 1 over cosine of alpha times sine of alpha. Minus sine times sine again is sine squared of alpha. All over cosine times sine. Cosine of alpha times sine of alpha. And then we've got our common denominator, so we can put these together. This is going to equal 1 minus sine squared of alpha over cosine of alpha times sine of alpha. But 1 minus sine squared of alpha is equal to cosine squared of alpha all over cosine of alpha times sine of alpha. You can say cosine squared divided by cosine is just 1 cosine, or you could really, if you really wanted to, you could say cosine squared of alpha is cosine of alpha times cosine of alpha, and then divided by cosine of alpha times sine of alpha. Cosine divided by cosine is just 1. We're left with cosine alpha over sine of alpha, but there's a quotient identity for that. Cosine over sine is the same as cotangent of alpha. Let's do 1 more, and then we will call it a day. Sure, we'll try. Which one do I want to do here? Yeah, we'll do that one. So let's try. I'm gonna try and switch it up a little bit so it's sure. I think this will work out fine. If it doesn't, we'll fix it. So let's try cosine of beta over. I'm a little worried here, but we'll make it work. Cosecant of beta minus sine of beta. And again, so really the only thing I think to do is write things in terms of sines and cosines. That's kind of like my only go-to move, really, if there isn't anything else obvious. So I'm going to rewrite this as, well, specifically cosecant is going to be 1 over sine of beta. And then sine of beta is going to be, well, just sine of beta. But I'm going to want to get a common denominator. So I'm going to write that as sine of beta over 1. Up on top, still cosine. Cool. So now, here I need to multiply by sine over sine. I feel like I switched this up in a way that is not as exciting as it could have been. Oh, well. Such is life. So multiplying that by sine over sine, and it's a little messy, apologize. That's going to be cosine of beta on top. On the bottom, I have 1 over sine of beta minus sine squared of beta over sine beta. So then that's going to equal cosine of beta still on top over 1 minus sine squared beta over sine of beta, apologies. And this is a perfectly good time to copy dot flip or whatever people like to say. I might do one more simplification first. I can write this as cosine of beta over 1 minus sine squared beta is cosine squared of beta over sine of beta. I don't know how you like to show this work personally. What we're really doing is we're just multiplying the top and bottom by the reciprocal of the bottom. So multiplying the bottom by sine of beta over cosine squared of beta, doing the same to the top. Sine of beta over cosine squared of beta. Cosine squared beta times sine beta over sine beta times cosine squared beta. Those are the same, so you just get 1. So we're gonna end up with a fraction where it's whatever's on top, cosine of beta times sine of beta over cosine squared of beta, all divided by 1. You don't need to show that. Like, you could totally jump straight from here, or sorry, I guess from here to where I'm in right now, which is just cosine beta times sine beta over cosine squared beta. It's perfectly fine to go straight from this step here. You don't have to write all this copy dot flip stuff, and you can just be like, oh yeah, I'm going to multiply by the reciprocal of what's in the bottom here. So multiply by sine beta over cosine squared beta. And then I'm going to write this as cosine over 1. Write this as 1 fraction cosine of beta times sine of beta over 1 times cosine squared is just cosine times cosine. We cancel a cosine, or cosine divided by cosine is equal to 1. So we're left with sine over cosine. I should say sine of beta over cosine of beta, which is really tangent of beta. All right. That's all I've got. I hope you have watched this video before class on Tuesday. We don't have class on Monday. Have a lovely long weekend, or I hope you've had a lovely long weekend, and I look forward to seeing you all on Tuesday. Bye.